Okay guys, so this part 3 for the video lecture will be the last part. Okay, I will show you how to resolve the question, the example of questions that are normally been asked during exam assignment and so on lah. Type of the questions that will be asked. Okay, first, the systems. So obviously it's a digital system since we have a converter here, right? A converter. We use a zero order host. Okay, and then first thing first, you have to know how to find the open loop transfer functions. Open loop transfer function. So what is open loop transfer functions? Okay, now examples, yeah. Let's say you have one systems, okay, normal systems, something that you're familiar with, RS, and then you have one system, GS, okay, and then the output, YS, and then you have one feedbacks, submissions, and plus, minus, RS, GS, YS. So for the open loop transfer functions, first thing is that we cut the wire just before the negative sign here. So it starts from RS to this point. So what is the systems that we pass through? The path. Okay. So from here, for the open loop transfer function for the system, starting for the RS to these points is GS. Okay, GS. Okay, another examples. What if the system is something like this? Okay lah, nanti kan you refer kan. So sini RS, and then this is GS, and then the output. Itu lagi systems. Sorry. G1S, and then katalah G2S. Okay, and then the output, and then we have one feedback. HS is here. Then the feedback, negative, positive sign. So the open loop, what is the open loop transfer function for this particular systems? So first thing is that we cut the wire just before the negative sign. So start from RS to this point. So the systems, the path is open loop transfer functions is equal to first G1S times G2S times HS. So here is the open loop transfer function. Okay, now for our system, this is example 1. Example 1, example 2, how we find the open loop transfer functions. So now for our system, our questions, okay, given these systems, okay, I think better I draw it again. Sama, so RS, a quick one. So it has a sampling T. And then zero order mathematical equations, 1 minus exponent ST over S. The system 3K S plus 1. Okay, YS and negative plus. Okay, so now the questions. What is the open loop transfer functions, similar as previous examples. We cut the wire just before the negative sign, starting for RS to this point, okay, to this point. So the open loop, we made these functions and these functions. So the open loop transfer function for this particular system is equal to 1 minus exponent st over s times 3k over s plus 1. So this is the open loop transfer function. But everything is in the digital forms. So this solution is in the continuous or the time domain. So first you have to convert it. After you get the open loop transfer functions, you have to convert it to the digital forms in order to analyze the systems. Convert pula. Okay, kita convert. Okay, to the digital systems, to digital forms. Digital forms. Kat sini negatif ni. Negatif. First knowledge, Z is equal to exponent ST. So we convert it from frequency domain to the Z transforms by using this conversion. So here we have exponent minus ST. And we know that Z is equal to exponent ST. Therefore, exponent negative ST is equal to Z minus 1. Okay. So from here, okay, the open loop transfer function 1 minus exponent minus ST over S 3k S plus 1. Okay, we convert it to the Z transforms. We get 1 minus Z minus 1. Okay, terlebih pula ni minus times 3k S plus 1. Okay, so we already convert these things, but we haven't settled this part yet. Okay, we still have a S represent the frequency domain. Okay, so now we have 1 minus Z inverse times 3k S plus 1. So obviously for this part we will use Z transform tables, okay, in order to convert from frequency domain to Z transforms. However, in order to use the Z transform tables, you have to use the partial fractions, okay, from here. So 3k S plus 1 is equal to A over S plus B S plus 1. So now you have to determine the value of A and B. Okay, so this is how I do it. I think Dr. Haziza has a different approach. So you either can use his approach or mine. Okay, so for partial fractions, this one's times A times S plus 1, B times S. So we get 3k equal to A S plus 1 Okay, so we make the denominator for left hand side and right hand side similar. Okay, so we have to times s and s plus 1, right? So s plus 1. So s times s plus 1, e times s plus 1 plus b s plus 1 times s. So b times s. So the first equation you get is the denominator is equal to 3k equal to a s plus 1 plus bs. So in order to make these functions 0, okay, so s must equal to 0. So 3k, when s equal to 0, 3k equal to a 0 plus 1 plus 0. So a equal to 3k. In order to make these functions 0, this function 0, so s is must equal to negative 1. So when s equal to negative 1, so 3k equal to a negative 1 plus 1 plus b negative 1. Therefore, 3k negative equal to b. Okay, so that's the value of a and b. Okay, so now we replace it in the first equation. I think this is 1. Okay, so from 1 we can write it down as a 1 minus z inverse times mana dia a equal to 3k. So 3k over s minus 3k over s plus 1. So this is how we write it down. And then we rearrange the equation. Okay. So we put 3k outside the bracket. So we get 3k 1 minus z inverse 1 over s minus 1 over s plus 1. Okay, so Chun, now we want to compare with the ZTransform tables. Okay, kita tukar warna sikit. So here is purples and then here is blue. Okay, now purples. Then we refer to the Z transforms 1 over s. Here is equal to this equation if you want to convert to Z transforms. And then 1 over the blue color, 1 over s plus 1. So these forms where a equal to 1. So we convert to this form. Okay, so we already refer the Z transform tables. We know how for each function how we convert to Z transforms. Okay, so we substitute in the equations. So the open loop transfer function ni starting open loop transfer function in the digital form, so is equal to 3k y minus z minus 1 times purple color 1 over s is equal to 1 over 1 minus z inverse. Okay, minus blue 1 over 1 minus exponent minus a. A is equal to 1. So 1 t. So t lah. T z minus 1. Okay, so this is how we represent the Z form or Z transform. Okay, so now from here you want to simplify the equations. So so we times 1 minus Z minus 1 in the bracket. So 3k times 1 minus Z minus 1 over 1 minus Z minus 1 minus 1 minus Z inverse 1 minus exponent negative t Z inverse. Okay, so now this become 1. So 3k 1 minus 1 minus Z minus inverse over 1 minus exponent minus t Z inverse. Okay, so you want to expand the equation from here. So we will get 3k. So here 1 is equal to 1 over 1 minus exponent minus t Z minus 1 over 1 minus exponent minus t Z minus 1. Z minus 1. Okay, I think I have to explain this. Yeah, it will be, someone will ask how we convert from 1, how we get 1, how we get this equations. Okay, so I just explain it. So here, from here you write it down, you will get 1 minus exponent minus t Z minus 1 minus 1 minus Z inverse over 1 negative exponent negative t Z inverse. Okay, so from here negative k 1 minus exponent minus t Z minus 1 plus Z minus 1. Okay, 1 minus exponent minus t Z inverse. Okay, from here 1 minus 1 sẽ become 0. Kan? Ini become 0. So you will get 3k Z inverse minus exponent minus t Z inverse over 1 minus exponent minus t Z inverse. So from here you will get 3k Z inverse times 1 minus exponent t over 1 minus exponent negative t Z inverse. And then we want to convert it to the Z's relation or conversions, not Z inverse. Okay, so how we do it? So here is 3k 1 minus exponent minus t over Z, right? Z minus 1 equal to 1 over Z, sayang. Okay, over 1 minus exponent negative t over Z is from here. Okay, so we arrange the equations. Okay, this thing is become Z over Z. Okay, so you will get here, matematik nak tunjuk ke? So 3k 1 minus exponent minus t over Z, okay, times Z over Z minus exponent negative t. So Z 1 1 So now the simplified equation, so we get 3k 1 minus exponent negative t over z negative exponent t. So this the open loop transfer function. Baru sampai open loop transfer function. Okay, so this the open loop transfer functions. What if the question asks, okay, let's see the questions something like this. Okay, so compute the open loop transfer function if t equal to 0.3. So what you have to do, just replace the value of t in the equation that you get. So you get open loop transfer function equal to 3k 1 minus exponent negative t over z exponent negative t. Okay, so it's give t equal to negative 0.3, sorry. So substitute the equations. So you will get 3k 1 minus exponent negative 0.3 over z exponent negative 0.3. So use the calculator here. And then you will get from here 3k 1 minus exponent negative 0.3 0.777k over z minus 0.741. Okay, now we go to the second questions. You already have the open loop transfer functions or the questions that I already changed it to compute the open loop transfer functions if t equal to 0.3. So sorry. So the second questions, the range of k to make the systems stable. So what is the range of k in order to make the system stable? So previously we already compute the open loop transfer function when t equal to 0.3, and then here is the equations. So open loop transfer function when t equal to 0.3. So this is the answer. Now we want to find question 2, range of k in order to make the system stable. So in order to get the range of k first, you already obtained the open loop transfer functions when t equal to 0.3. Okay, done. And then in order to find the range of k, you have to find the closed loop transfer functions. Okay, so how you want to convert from open loop transfer function to closed loop transfer functions? By using the equations or the formula gs over 1 plus gs. Gz dah sekarang. So gz over 1 plus gz. Okay, where gz is equal to open loop transfer functions when t equal to 0.3. So you substitute the equations. So 0.777k over z minus 0.741 1 plus 0.777k z minus 0.741. So you rearrange the equations and you will get closed loop transfer function is equal to 0.777k over 1 over Z minus 0.741 plus 0.777. Okay, so this is the closed loop transfer function for the system. So in order to make the system tables, okay, you already have obtained the closed loop transfer functions. Like 0.777 key Z minus 0.741 plus 0.777 key. So in order to make the system tables for the digital system, you have to make sure that the unity circles -1 1 -1 1. So the unity circles, so this reals imaginary, so you have to make sure that the location of the pole is within the unity circles. Okay, so you have to make sure in order to make the system tables, the location of poles is within the unity circles. Okay, within the unity circles. So the denominator, okay, is equal to 0 in order to find the value of poles. So Z negative 0.741 plus 0.777k equal to 0. So from here you will get Z equal to negative 0.741 minus 0.777k. So based on the equation of the Z, okay, here, so the value of the Z is on the real axis. Okay, something here. So what is the range of K in order to make the systems, or the system is tables? The range of K. So in order to make the system tables, the value of Z must less than 1 and greater than -1. So we use this equation to find the value of K. So -1, Z is greater than -1, Z is negative 0.741 minus 0.777k, and Z must less than 1. So here we have two conditions. Okay, condition 1 and condition 2. Okay, for condition number 1, -1 less than 0.741 minus 0.777k. Okay, so we rearrange the equations. You get negative 0.0741 to the left, so -1.741 less than negative 0.777k. Okay, so therefore we just change the locations of K to left and right. So you get 0.777k less than 1.741. It's negative and negative. So therefore K is less than 2.24. Okay, this is condition number 1. And condition number 2. Negative 0.741 minus 0.777k less than 1. Okay, so we change the location. Negative lah, positive, sorry. Positive or negative here? Sorry, ini is positive. Okay, so 0.741 minus 1 less than positive 0.777 K. So therefore, K negative 0.333 less than K, or K is greater than negative 0.333. Okay. So the range of K in order to make the system stable, okay, range of K in order to make the system stable, we have to choose the value of K is K less than 2.24 but greater than negative 0.333. However, please bear in mind that the range of K must within 0 to infinity. So K less than 0 but greater than K less than infinity but greater than 0. So it means that K must be positive value. Okay, so this is the general information everybody know. K must be the positive value. So now from here, so we change a little bit, and the range of K in order to make the system stable is K is greater than 0 but less than 2.24. Okay, so this is the answer for the range of K in order to make the system stable. Okay, so let's say let's give a few questions or a few value of K. It give that K equal to 1, 2, 3, 2.25. So in order to make sure the system is stable, you have to check whether the value of K is within the range. So first, if K equal to 1, so the system stable. If K equal to 3, the system is unstable because is not in the range of the K value. Okay, so I think that's all for digital control systems. I have already chunk into 3 part 1, 2 and 3. So it's a very detailed explanations, but the idea is there. We already cover how to convert from from analog to digital systems, and then how we find the value of K in order to make the system is stable. However, please bear in mind, first you have to find the open loop transfer functions. Okay, when you get these type of questions, first you have to find the open loop transfer functions. Okay, so from here, in order to find the range of K, you have to convert from open loop transfer function to closed loop transfer function. Okay, so I did show one examples. I will give a few exercise. Okay, please do it, and then we will discuss, or I will give the solutions in order for you to check either you can find the correct answer or get the correct answer, or etc. Okay guys, so I think that's all for digital control systems. So thank you. So I think the list. Okay guys, thank you very much.